Hi everybody. Well, let me tell you, there's nothing like the feeling of going all the way through your notes and realizing for some reason the microphone had an error. Hopefully I'm actually recording this time. I guess I won't know until I try and collect the video. But we are going back to the idea of capacitor. We're moving on with electricity, focusing on the capacitors today, working our way towards those two problems that I'm assigning right here, number 28 and 29. They are going to be very straightforward using one equation, and we'll get a little practice before we're done. Alright, now if you remember, we have a situation right down here with Mr. Eggshen where there's charge on one side, charge on another side, and energy is stored in between, and that is the definition of a capacitor. But, you know, we want something a little bit more precise, I think. So, if we take a look, these are all different types of capacitors. Each device performs the same basic function, it does it a little bit differently. So, as far as our definition of a capacitor, it's going to be a device that stores electrical energy inside an electric field using electrical charges. Alright, so it's a device that stores electrical energy inside an electrical field. It is passive, which essentially means that it's not going to be shipped to you from the store with charge already. That would be very dangerous. If you think back to the quick clip I had of me sneaking up on Mr. Stanton with the stun gun, that's a capacitor. If you were to ship a capacitor with 750,000 volts already stored, that's dangerous. That could be, well, shocking. Okay, and a great example would be the first time I showed that thing to Mr. Stanton, came up right next to him, said, hey, take a look at this, put it maybe this far from his face and discharged it. The shock was hilarious. The security camera footage actually caught him punching me in the chest. It was really funny. Let's just start with that. But a capacitor is going to be passive, which means it can't do anything unless it's hooked up to a circuit that will charge it. Alright, and it is a device that stores electrical energy using an electric field. Now, it's not the only device you know of that can store electrical energy, so why bother using a capacitor? Alright, well, because capacitors do things that batteries just can't. Alright, they can let go of its electrical energy at a different rate, and really that's where the kicker is. That's what they're useful for. Alright, but let's compare it. So, you're talking today about a capacitor. Again, it's going to store electrical energy in here. There are two ways to access the capacitor. We're going to call them terminals or leads. I prefer to call them terminals. But they're not the only electrical device that you know of that has terminals. Batteries also have terminals, that positive and negative. But a capacitor is going to function differently than a battery. Primarily in terms of how much energy they can store, and then how fast they can charge or discharge. So a capacitor does not store as much as a battery, but it charges and discharges much faster. So yeah, a battery can store more, but a battery will run that charge out, let go of all that electrical energy over hours, days, years, depending on what you're using it for. But a capacitor, it can charge and discharge however much energy it has in a millionth of a second. So it can be much more useful for that fast charge. To give you an example, I want to show you a quick simulation. The simulation will be using one of the types of capacitors we're going to be familiar with. We're going to talk about a parallel plate capacitor. It has one metallic material that can store charge, separated from another one that can store charge. They never touch. Alright, the distance between them is uniform. If you have a positive charge here and a negative charge here, what do you have in between? Well, it's an electric field. What do you store in an electric field? Electrical energy. The other kind is a cylindrical capacitor. That's the kind we'll actually use when we build materials, but they're really going to be the same thing. You have a conductor separated from another conductor by a certain distance. In this case, that yellow right there, that's called a dielectric. It's just something that can't conduct electricity, so these never actually make contact. The only way you get from one plate to the other plate is through those terminals we were talking about. That's what these would lead to. Alright, so in our quick simulation, talking about a capacitor and how they function, this would be a parallel plate capacitor. I can store charge on it by applying a voltage. So right now I've got 16 positive charges here, 16 negative charges here, and you have an electric field between them. Now if I were to go to a situation where I want to take that charge and light a light bulb, well, how else can you light a light bulb? With a simple battery, right? So if I have one kind of device right here, the battery, that stores electrical charge and electrical energy, if I close the switch, the charges slowly move and provide a constant light to the light bulb. And that will go on for hours, depending on what kind of battery we're talking about and what kind of light bulb we're talking about. A capacitor is not going to be the same thing. So let's break this. If I go over to what a capacitor would look like in a situation with a light bulb, first I've got to set this thing up and charge it. So I connect my capacitor to the different terminals of a battery. The positive terminal stores a lot of positive charges on this one. The negative terminal stores a lot of negative charges on this one, and they can't move. There's no way for the two to connect, so I have a huge amount of energy stored in this electric field. As soon as I move the terminals over, I'm going to send that electrical energy through the light bulb. I'll use it to power the light bulb. But notice, there's a difference. The brightness is going to be different than that constant brightness from the battery. The time it takes to light, or the time it will light for, is going to be completely different as well. It gets very, very, very bright, and as it's running the power, or the energy is going through the light bulb, notice what happens to the charges on our plates. They're dissipating, and the bulb gets dimmer and dimmer and dimmer, and eventually, when there's no charges left, the bulb is going to be completely off. So capacitors, you can release a whole lot of energy at once, but it won't be for as long as a battery. All right, and as far as charge time, once this thing actually runs out, I can instantly recharge this by connecting it back to the battery. It doesn't take a long time. I don't have to plug it into a special charger for hours and hours and hours like you would your cell phone. I just simply hook it right back up to the battery, and bam, it's fully charged, and there I go again. So I can charge quick, discharge very quick, large amounts of energy. Big difference between the battery and a capacitor. Now, if we look back to our two electrical devices to store electrical energy and look at our capacitor, it's going to be measured differently than, say, a battery. Batteries are measured in volts, and that's where it stops. But with capacitors, we measure capacitors in something called capacitance. And that is a whole new thing for us. But it's part of the equation we're going to be using for our homework. So the capacitance, C of a capacitor, is a ratio of the magnitude of the charge, so stored on either plate of the capacitor, on either conductor, to the magnitude of the potential difference between the two conductors. So in that previous setup, I had what, a 1.5 volt battery. Well, that would be V. I have 1.77 picofarad capacitor. That's this parallel plate capacitor right here. And by connecting these two, I store a certain amount of charge, capital Q, on each plate. Alright, so our equation, capital C stands for capacitance. It's measured in farads. Alright, now it sounds like ferrets, but it's not ferrets, it's farads. Okay, and usually it's not going to be very large units. It's going to be something like, let's see here, picofarad for a really small capacitor. So now pico means times 10. Sorry for my poor drawing skills, to the minus 12th. Alright, or it could be nanofarad, which we used nano before, or it could be microfarad. Now nanofarad, this one, is times 10 to the minus 9th, remember? Whoa. And then micro, that's times 10 to the minus 6th. Wow, it's just painful to watch me draw. Alright, now what does that mean? Pico, nano, micro, that means small. Alright, so these are going to be very, very small charges, or small capacitors. Again, microfarad. Alright, microfarad, not microfarad, not a really tiny cute farad, but a really small unit of charge. Here's our important equation. Capacitance is equal to the charge stored in your capacitor divided by the voltage applied to the plates. Alright, now if I had to guess, the difficulty we're going to have here, even though it's just a 3-variable equation, is the fact that we are using a capital Q instead of a lowercase q. And capital Q, what does capital Q measure? It measures coulombs. How do we write coulombs? Capital C. These two capital C's are not the same thing. So this is the unit of charge, and capacitance has units in farads. Alright, that's going to be the confusion. This is a variable for capacitance. This is a unit for charge. So that's probably where we may have some difficulty, but we'll get through it. Now these devices, these capacitors that are used to store electrical potential energy in the form of charge inside an electric field. By the way, that's another big difference between a battery and a capacitor. The capacitor stores charge in an electric field, where a battery, just like you learned about in chemistry, that stores it in terms of chemical energy. Alright, so these things, they don't all look the same. These capacitors have different sizes, different shapes, and it's all about what they're used for. Alright, so the devices are going to vary based on use. If you want to store a whole lot of charge, you're probably going to need a bigger capacitor, and let me show you why. Now there's several equations that we're going to have, but again, we're focusing on this one right now. Capacitance is equal to the charge stored in the capacitor divided by the voltage applied to the capacitor. Now there are ways to change that capacitance, namely the size of your capacitor and how far the plates are from each other. And that's where this equation comes in. Capacitance is equal to the permittivity of free space. Not even going to give you what that is because we're not going to use this equation. But the permittivity of free space, that space in between the charge and in between the charge plates, multiplied by the area of the plate and the distance between them. What you need to know until you do the lab, the simulator lab that I'm working on, is that if you change the separation, so like these plates are really close together, if I pull them further away, that means D in that equation, D is going to be a larger number, so capacitance, this measurement right here, will decrease as the plates get further and further away, and look at that, it decreases as I pull it away. Also, area, as I decrease the area, we're also going to decrease the capacitance, how much charge the thing can store, how much energy can be packed inside of it. Alright, that's a simple relationship for right now. If you decrease the distance between them, more capacitance, more energy. If you increase the size of the charged plates, more capacitance, more energy. And that is why capacitors are going to have different sizes and shapes, and they'll look slightly different. Okay? But again, focusing on this equation. Now the goal is eventually to put a capacitor in a circuit you will build. We will find a way to do that. We will. Alright, so we have to understand how to look at schematics when we're building a circuit. We need symbols. The very first symbol I'm putting in your toolkit of symbols is the capacitor symbol. Alright, namely this guy right here. So this is a symbol for a parallel plate capacitor. Even if we have a drum capacitor where they're kind of rolled together, like in that first picture, it's still basically a parallel plate capacitor. This one right here is a polarized capacitor. We're not going to be working with polarized capacitors, so we're going to ignore that symbol for right now this year and just focus on parallel plate capacitors. So whenever you see that, that is a device that's going to store charge in an electric field, store electrical energy inside an electrical field. Okay? Now even though we're not using that equation, capacitance is equal to the permittivity of free space multiplied by the area of the capacitor divided by distance, we're not focusing on that one. There are some electrical energy equations dealing with capacitance I'm going to make you responsible for. Again, I'm putting them in here, so this is a record of notes. You can take actual notes on this, or you can constantly look back in these videos. I think taking notes might be a better option. But here are the other equations that you're going to be responsible for, we'll be using later on. Again, not on this first assignment, but since a capacitor stores electrical energy, I might as well show you how they relate to the electrical energy they store. So I have a parallel plate capacitor here, plate A, plate B. There's a voltage applied to A and B, that's VAB right there, that allows it to store charges. So this has positive charge, this has negative charge, and hey, there's going to be a field between them. So this is our parallel plate capacitor. If I want to know something about the electrical energy, the electrical potential energy of that parallel plate capacitor, which is basically the electrical work done between the two plates. Won't focus on this, want to focus on terms of these three variables. I could determine the electrical potential energy of this capacitor if I know the voltage between the two plates and how much charge is stored in the capacitor. So 1/2 the voltage between the plates times the charge on the capacitor will give me the electrical potential energy stored inside of it. Or the charge on the plates squared divided by twice the capacitance. And again, capacitance is measured in farad. That will give me the electrical energy. And then finally, if I take 1/2 the capacitance of this capacitor, which again is just going to be a number given to you in farads, and I multiply by the voltage applied squared, I'll get how much energy is stored inside there. All right, so those are other equations we will be using in the future, and I'll reintroduce them one at a time as we do use them. But what I want to do to finish today is actually just a simple problem that is much like your homework problems. So, I have a sample problem right here. I have a parallel plate capacitor set up right here. I have a voltage source applied to it. So if we have a 4 microfarad parallel plate capacitor like the one shown here, and it's connected to 1/2 volt battery, so I have this voltage set to 1/2 volt, how much charge in coulombs is stored on this capacitor? All right, and again, we're just going to use this equation right here. Capacitance is equal to charge divided by voltage. I want to find the actual capacitance. I want to find the actual charge given the capacitance and voltage, so I just got to rearrange the equation using algebra. And now we're going to see me draw on this, and it's going to look, well, pretty choppy. So Q for charge, again, Q is measured in coulombs, is equal to capacitance measured in farad times the voltage across the capacitor, so the voltage used to charge that capacitor up. And now I'm going to plug in the numbers. So, the charge is equal to our capacitance, which is 4 micro means times 10 to the minus 6th, not microfarads, tiny little farads, microfarad, so minus 6. And then I'm going to multiply that by the voltage of 1/2 volt. I got to find a faster way to write. If only I had a way. Whew, that took a while. Fortunately, the math is a lot simpler. All right, so I'm going to multiply the capacitance times the charge, and it gets to be really simple. It's just going to be 1/2 of that 4 times 10 to the minus 6, so it's going to be 2 times 10 to the minus 6th, and now I'm not finding anything but charge. Charge is measured in coulombs, capital C. Again, this is the unit. That is a variable. This is a unit of charge. So this is how much charge is stored on that particular capacitor given the information I gave you. All right. So your homework is going to be very similar to that, just using that simple equation. I'm going to assign these notes. Every time I upload notes now, they're going to be an assignment. I want you to watch them. I want you to go through them and take a few notes on them. Refer back. Tuesdays and Thursdays, I'll have office hours when I upload this assignment and your 2 problems. I'll also load into that same area the link to the Google meeting. All right, and it's going to be from 12 to 1 o'clock. Trying to find a place where people are going to be awake and sign on if they need to ask any questions. You may not have any questions for this first one. You can still sign on to say, hey, watch the video, didn't understand what you're talking about here. All that works. I'll go through it with you and make it as simple as possible. Okay, so I'm uploading all this right now. I hope everyone has a great Monday and prepares for a really good week. Miss seeing you. Hope to see you again soon.